Hey. We're at the next part of what we still call permutation combination per se, kind of, sort of. The combinations comes back into play in this one, so hopefully you understood at least how to make combinations or how to put numbers in the calculator to find combinations, because that's what's going to come into play here. We're going to call this binomial theorem. And with it, I'm going to go ahead and give you some things to help you to understand and hopefully remember. And hopefully you've already watched the video about Pascal's triangle, Pascal, because he has a triangle that we're going to look at really briefly. And then we're going to move on to the whole thing with combinations, permutations. So this is binomial theorem. So first off, before we even do all of that, we have a new vocabulary word, which is binomial. And that just means that you have two terms. Bi meaning two, binomial, bi. And then there's a binomial theorem. And binomial theorem means that we are just expanding those binomials. So just like we did with x plus y quantity squared, you can expand that out using FOIL and getting all the values and all that good stuff. Even with the cube part, all of that's important. That's binomial theorem. So here, to help us with binomial theorem, we have this thing called Pascal's triangle. And you might have seen it in your math classes before, or last year, any time that you did the math before, you might have seen it. But I'm just going to go ahead and show it to you really quickly, do an example with it, and then from that point on, we're not going to do Pascal's triangle anymore. But I just want to pull it back for hopefully you saw it last year, pull it into this year, and then move on from there and take up to the next notch, which is advanced functions way. All right, so Pascal's triangle. And I'm going to pull this over here onto the Elmo because I think it writes better, I think, on this. So Pascal's triangle. All right, so Pascal's triangle, that's this wonderful thing. It always starts off with 1 right smack dab in the middle, the top middle. So if you look at my paper here, pull out just a little bit, that's like smack dab almost in the middle. It's not necessarily in the middle, but almost. So it starts off with 1 there, and then the next row has 1 and another 1. On this next row here, again, we always start off with 1 at the beginning. We always end with 1 at the end, every time. And we just have to figure out what goes on the inside. Starts with 1, ends with 1. So if we look at it, here, if we add 1 plus 1, that gives us 2. So 1, 2, 1. Here, again, next one, we start off with 1, we end with 1. So we add 1 and 2 together, give us 3. We add 1 and 2 together, that gives us 3. Okay, not bad. And this continues on forever until eternity. It's infinite. So just like with our infinite numbers, infinity from the beginning of the semester, infinite sequence, infinite series, this thing goes on forever and ever and ever. So it never stops. And it grows and grows and gets huge. So just going to do one more line here. So I'm going to put 1 in front, 1 in the back. Again, 1 plus 3 is 4. 3 plus 3 is 6. 1 and 3 is 4 again. And then 1 on the back. Now, this helps us whenever we have to deal with expanding things. So we've already talked about x plus y squared. And we know that if we were to write this out, we'll get x squared plus 2xy plus y squared. Because we already know that. We already talked about that. Already dealt with that. Now, with it, if you notice this, there's like an understood 1 right there and understood 1 back here. So if we were to kind of look at this right here, what we did, and look at our triangle, Pascal's triangle, and remember Pascal's goes on forever and ever, doesn't stop at 4. But if we do that and match them up, there's a 1, 2, 1, and there's a 1, 2, 1 right here. So really, Pascal's triangle gives us the coefficients for each one of these terms in our number and our expanded part. So Pascal's triangles helps us with that so we can get it done quicker. So we don't have to worry about doing all this work to expand it, because when we get to numbers like to the 12th power or the 24th power, because final exam, they like doing stuff like that, giving the 24th power, and they say find the middle term. You don't have time to multiply that all out over and over and over again to get that 12th time and then find the middle term. You don't have enough time for that. So let's use Pascal's triangle, or what we're going to do later on. All right, so with that being said, we have all of this going on. And another way of writing this, well, we keep it like this right now. I'm going to change it on the example one. I'm going to change how we write this in example one, but it's going to be cool. But again, Pascal's triangle just shows you the coefficients that you need. And so this right here, this first line is considered the 0 power. The second line is the first power. So something to the 1 power. This is the second power squared. So that's what we have right here, squared. This is the third power. And this is the fourth power. And then so on and so forth, and goes on forever and ever and ever. So if you have something to the fourth power, that means these are the coefficients for your numbers. And then we explain the rest of it later on. But that's Pascal's triangle. That's it. Not hard. We can do this. So let's go to an example where we do Pascal's triangle.